learned fatty acids, and we have learned triglycerides, we have learned phospholipids, what else? Sphingolipids, and then subsequently the steroids, right? So we covered 5 of them now. So now we're going to talk about what's the importance of this lipid, or what kind of thing that they form inside our body, right? So the first one is mast cells. Okay, do you know what mast cell is? Okay, not yet, right? So you learn this a little bit more detail when you learn about drug delivery and formulation. But generally, in our body, our body can also form mast cells. So these mast cells is when you have, okay, the one in maybe just roughly explain. So the one in red, right, usually is referring to the oxygen group, which is the polar group. Okay, polar group. And then the white color is actually the carbon. Okay? So it's your hydrocarbon, which is the chain. So you can just imagine that this is actually like a phospholipid. You have a phosphate group or alcohol, the oxygen group, or phosphate and oxygen, and then followed by the alkyl chain, right? So when you put this great number of phospholipid inside what do you call it? Inside a bowl of water, for example, where all the environment is actually water. So what happens is that this particular what do you call it? Okay, this is probably not a very good example, but I just want to show you that generally all this white color subchain, right, when you put inside water, the polar group will, because we know the polar group is actually water loving group, so it will actually move towards the water, whereas the hydrocarbon group, which is non-water loving or water hating group, will try to clump together to protect themselves from the water environment. Can you imagine? So, okay, how should I put it? So, can you imagine that if you have oil and water together, right? Oil and water together. So, what will happen? Will the oil mix with the water?
No.
No, right? So, if you introduce some kind of energy to it, right? The oil will come together, right? And form a globule. Am I right? Okay, so why it forms together to form a globule? Because if the water will only want to interact with the water. So it forces the oil to actually group together so that they can interact and form a globule, right? So the outside there will be just water. Okay, so it's like a forming globule. So mast cell is something like that. So you have a lipid, you know it's like a oil, so it will actually potentially just group together to the center, and then the water, the polar group of your phospholipid will actually surrounding the outside of the thing exposed to the water. Right? Maybe this is not a good indicator. Okay, so another one is lipid barrier. So the difference between mast cell actually happens when you have only a single hydrocarbon. But lipid barrier is when you have the double such that what you see in the phospholipid. So let me show you this instead. Right? So probably this is a better. Actually, I wanted to show you the video, but never mind. So this one here is actually the mast cell. So you can see that there's a single hydrocarbon followed by the polar group, and this is actually the outside environment is actually your water environment. Okay. Lipid barrier is when this phospholipid, which you have two tail and one polar group, if you remember, right? Because it has a phosphate group on one of the cholesterol network, and then another two carbon is actually attached to the alkyl chain, so it forms the structure that looks like that. Right? So that's your phospholipids. So if the phospholipid is put together inside a solution, then it will actually forms a lipid barrier, as you can see over here. But if this particular lipid barrier, if you have a lot of phospholipid, then it can then forms a double layer of lipid barrier, which will actually enclose together and forms a vesicle that is known as liposome. So this liposome is not it's actually a model that people use to study the cells, because our cells also have this lipid barrier, and then thereby in the inside, here is actually water, right? Or cytoplasm in your case. Okay, so that's the different forms of how lipid can form inside our body. So, any questions? Can follow? Okay. All right. So next is the properties of the lipid barrier. So generally, lipid barrier are fluid, right? As I mentioned, it's not something that is stagnant. It's quite fluid. It can move around. Right? It's always move around. And the way it moves is that the lipid barrier it tends to move at a lateral position. So that means that if you have an upper leaflet and a lower leaflet, so the lipid barrier, the phospholipid actually move rapidly across at the same layer. It won't flip-flop frequently, right? So as you can see over here, the flip-flop or the transverse diffusion is very, very slow. So rarely happen because it needs more energy, right? But the polar group needs to go to the center, which is very hydrophobic before it can jump over here, which is a bit more difficult. But it can easily move left and right, okay? Because there are quite similar properties among them, right? Okay, so the fluid properties are highly dependent on the transition temperature. The transition temperature here means that it's a temperature whereby it will change from a gel to liquid or liquid to gel, whichever you want to say. So if it's below the transition temperature, we know that it will form gel-like solid. Whereas if it's above the transition temperature, then it's going to form a liquid crystal. Right? So this is similar to what you kind of learned about the melting point earlier on. So if it's something that is, if it's very, if the chain, for example, if it's very long, or if the saturation of the fatty acids is there, then the transition temperature will change up. Okay, so for example, if your chain is longer, that means the interaction will be more, right? If the chain is longer, the interaction will be more. So when the interaction is more, the temperature will be higher because you need a higher temperature to convert it from solid to liquid. The melting point like that, right? And similarly, if the degree of saturation is higher, it means you have higher saturation. Higher saturation means it's more closely packed. If it's more closely packed, means that the interaction is stronger, so you need more energy to actually break them apart. So the transition temperature will also be higher. I follow? Okay. So it's just like melting point. Right? And another thing is, if you notice, I mentioned earlier on that the lipid barrier can also constitute of other things apart from the phospholipids. There's also cholesterol. The cholesterol, if you see here, the cholesterol can be inserted as part of the phospholipid barrier. And we know that cholesterol is very rigid, right? Because of the 4 rings. So it is less flexible compared to the alkyl side chain, so it's very rigid. And because of its rigidity, right? So imagine if, let's say, you have this lipid barrier here, which is at a very, if the vessel is already below the transition temperature, which is already in the form of solid. And if you introduce the cholesterol inside, so what happens is that you actually break the orders of the packing, right? When it breaks the order of the packing, so it will actually increase the fluidity of the lipid barrier. Do you understand? Do you want me to repeat again? Okay, so when below the transition temperature, we know that the lipid barrier will form solid, right? Because it's well packed. Okay. So when you introduce the cholesterol inside, cholesterol will actually break the orders, correct? You will prevent the ordering of the lipids. So when you prevent the ordering of the lipids, that means it actually increase or decrease the fluidity. Increase, right? because now it becomes less order, correct? Because you introduce something inside to break the order. Okay, so that's the role of cholesterol when it is below the transition temperature. If it's above the transition temperature, it has a different function. Right? When it's above the transition temperature, your lipid bilayer originally is already liquid in a fluid form, right? So having a cholesterol there will reduce this fluidity instead. Right? So the role of cholesterol in our lipid bilayer is highly dependent on the temperature it's in. Okay, so you just need to be aware of that. So it can be both sides, it can be both ways. Right? Okay, then this one you can read by yourself, but generally just to let you know that apart from the lipids and the cholesterol, there are also other things inside our lipid barrier. Purely like the proteins as well, oligosaccharides as well. So we have different protein that is embedded within the lipid. As you can see here, this is known as intrinsic protein. We also have a lipid-linked protein, meaning the protein which is covalently bound to a lipid, and this allows this protein to bind to the lipid bilayer. We also have a peripheral or extrinsic protein, which it has a lot of positively charged protein on the surface, which allows it to bind to the phosphate, the negatively charged phosphate group, non-covalently on the surface of the lipid bilayer as well. So there are many different types of proteins that you will learn in the future. But generally, the function of this protein can be as an ion channel or signaling purposes or whatever it is. Okay, so last slide. So this one, just to show you an example of a type of protein, we call it GPCR. Right, we wish you learn again when you learn other system. So this protein, if you notice, right, this lipid bilayer here will have protein, and then it will have different types of lipids, with cholesterol, with glycosphingolipid, right? And if this particular area, which forms a certain domain for certain function, with a constituents of protein and cholesterol and the glycosphingolipids, then this particular region here is known as lipid graph. So this is just another concept which you can learn by yourself later as well. So this is more awareness to you what is a lipid graph. Okay, so I think that's pretty much all I guess. Yes. Okay. So any questions that you want to ask? At least you managed to finish everything on time.